Alright guys, hello, my name is Andrew Pham, and today I'll be talking about the quadratic formula, the quintessential equation that dominates over high school algebra. In this presentation, we'll talk about the cultural backgrounds, the historical backgrounds on the equations, and then go over some tools that will assist us in the derivation, for which will then lead into the actual definition and derivation of the formula, and we will end with some discussion on the applications of the quadratic formula. So with that in mind, let's begin. So some contextual background in history. The quadratic equations have been around for a long time, all the way back since 1700 BCE, by the Babylonians, who found out the idea through their quest in solving for perimeter and area using geometric squares, for which they were able to develop the method of completing the square, something that we will use as well to help us in our derivation. But aside from that, nothing significant has happened in this realm until 3,000 years later, in 1825 CE, where Persian mathematician Al-Khwarizmi found and developed the first standard form of a quadratic equation, which is in the form ax squared plus bx is equal to c, where a, b, and c are all positive numbers, and the extension will be made to this idea to negative numbers and complex solutions will happen in the future, a few hundred years later, in 1545 CE, by Italian mathematician Cardano. He said, yeah, A, B, and C can now be negative, and also the solutions can be negative, but also complex. So this is what kind of started the start of complex analysis. And finally, we actually get to see the formula in all its glory for the first time ever in history in Descartes's La Geometrie, published in 1637. So with that in mind, let's go over some preliminary tools that will assist us in our journey to deriving the formula. First will be us defining what a standard form is. So let f be a quadratic function. Then the standard form of f is going to be given by ax squared plus bx plus c, where a, b, and c are all real numbers. All right, that's one. The next tool we'll discuss is going to be of completing the square, right? We're going to be using the completing the square algorithm to help us derive the formula, isolate x. So what is it actually? So consider the trinomial x squared plus bx plus b over 2 squared, and its geometric representation here. Notice that x squared is given by this x by x squared. Bx is actually not listed anywhere, but it's represented strategically as two b over 2x rectangles, where it's placed on the sides. So if you just consider these two rectangles in this square, you can almost see it's almost a perfect square. The only thing that's missing is this square right here, which has dimensions b over 2 by b over 2. Right. So that's important. This is a representation of this trinomial. But also take notice of the sides of the square. They're all x plus b over 2. So by taking side times side as also area, another representation of this quantity will be x plus b over 2 quantity squared. And this is the important observation that we need to make because that will allow us to isolate the x in our derivation. But before that, formally, if I wanted to complete the square of x squared plus bx plus c, I would have to add that small square at the end. But what can that small square be? Well, if you remember, it's going to be just the square of half of the x coefficient. X coefficient is b, half of that is b over 2, and the square is just raised to the power 2. But since we don't want to change the problem, we're going to subtract the quantity. We're adding a magic zero, essentially. Doing so, the first three terms simplify to x plus b over 2 quantity squared, just like in the picture. And the last two terms are just a collection of constants, which is another constant, which can be simplified later, and it doesn't really matter if it's in this form. But that being said, we are now ready to give the exact definition of the quadratic formula, as if we consider f to be any quadratic function, in standard form, we can find the solutions of f when f is equal to 0 by simply through this equation. X is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So what we're saying is, if I have any quadratic functions and I want to find the location of where the function crosses the x-axis or touches it, I can simply match the coefficients that it's of it in standard form and put it into this formula by substitution, and I should get out two values or one value as solutions. But where does this expression come from? Let's try to derive it now. So first we're going to let f equal to 0. That is ax squared plus bx is equal to c, or ax squared plus bx plus c is equal to 0. And then we're going to divide every single term by a, because remember, completing the square requires your leading coefficient to be 1. And we can divide by a because a is non-zero. And now we're going to apply the completing the square algorithm, which is we're going to take the x coefficient, divide it by 2, and then add the square on both sides. So b over a divided by 2 is just b over 2a. We're going to add b over 2a squared on both sides. Doing so, the left-hand side factors as x plus b over 2a quantity squared, and the right-hand side is again just a collection of constants. Here it should be very straightforward on how we solve for x. All we have to do is take the square root on both sides and then move this b over 2a over by subtraction, and then we'll get our result that we're trying to look for. So going through that entire algebra sequence, one can eventually find that yes, you'll eventually get the quadratic formula and its glory here as required. So now we have our results. What can we do with it? Is it simply just a root finder? Can we not do anything else with it? The answer is no, we can do more stuff with it. Not only is it a root finder, but it's also a root classifier. As if you guys are familiar with square root functions, you know of their domain restriction, as in I can only put in positive numbers underneath the radical number, or underneath the radical. If not, if it's negative, I'll net a imaginary constant term, I, which will lead in this case to a complex solution. So this term actually has a special name. This term, b squared minus 4ac, is called the discriminant. And whether or not the discriminant is greater than 0, less than 0, or equal to 0 will determine whether or not your solutions will be real or complex, but also distinct or repeated. So it's a very powerful tool. And you don't even have to solve for roots to be able to classify the roots. You can just test out this because you're just simply you're matching the coefficients of the standard form to this discriminant and see what value you get. For example, if it's less than 0, you know you're going to have two complex solutions. It's very helpful in root analysis. But other than that, we're talking non-mathematical reasonings, using the quadratic formula and learning how to derive it is an essential part to increasing one's critical thinking skills. It's very important for one to be able to give in like the tools necessary. So this formula is a tool. If I give you a tool, can you use it to help you solve an equation or solve a problem? The answer is yes. And so we help students learning how to use this are able to get some of those skills. It's also appropriately rigorous to derive because it turns out that cubics and quartics are significantly harder to derive, and a quintic is impossible to derive a solution for. So this is appropriately rigorous for most students in algebra. And yeah, very important. Aside from that, other applications in other subjects, quadratics are everywhere, from higher math to other sciences and even art, because quadratic equations produce parabolas, a conic section. So you might be able to see artworks that have parabolas in them. But yeah, a lot of different places. Anywhere a quadratic equation is, the formula will definitely follow. And with that said, I will conclude this presentation. So thank you guys for listening, and I'll see you guys next time.